Okay. All right. So happy Veterans Day for both of you. Okay. There are a lot of events out there, so I hope you enjoyed. Okay. Let me share my class notes so we can start. All right. So, what I want you guys just to move on for this week is that uh, more of an extended versions of a regression model. And what if we cannot really run, uh, regression model for the variable measurement wise and scalable measurement wise, and what might be the alternative method? So this week we're gonna go over multiple regression model and chi-square test. All right. So since we already cover a simple regression model, there are more than two-thirds of the basic foundations of a regression model. So multiple regression model is just some additional the information I left for this session, especially about F-test for the overall equation model. So let's talk about some extended understanding of multiple regression, how we need to understand the slope and how we understand those overall model significance. All right. As I mentioned that from last week, simple regression model, when we have a one single independent variable on dependent variable, so basically we wanted to know whether the slope for independent variable on dependent variable, whether it is statistically significant or not. But when we move to multiple regression model, we wanted to make sure multiple individual variables, especially multiple independent variables, together, they are important for our dependent variable. So multiple regression is we still have a one dependent variable, but we have a multiple independent variables. So we still looking at just try to trace linear relationship. So in other words, both independent and dependent variables, they're all linear, okay, all numerically in just nominal, I'm sorry, in over scaled variable. All right. So multiple regression model looking at the relationship between a single dependent variable with the collection of independent variables. That is the best way we can talk, describe it. All right. But when we talked about, beyond the simple regression model, in multiple regression model, we call that each slope or the each individual independent variable and how it is related to dependent variable as a partial relationship. All right, a partial coefficient or a partial slope, because by definition how each individual slope is statistically significant or not, it is determined by once you control all other independent variables. Still, this specific independent variable is significant and it still have a relationship with the dependent variable. So we oftentimes call the each slope as a partial relationship in the regression model. Okay. So, as what we talked about the beauty of regression model, we can come up with equation model at the end of regression model as what we practice on Thursday class and showed you. And once we find A and B or alpha and beta value, once you plug in and you can, okay, you can know this part, okay? So you can write up the simple regression model equation model. So once you have that, great thing is that now you plug in any independent variable, you know exactly what kind of a dependent variable and value you're gonna get, all right? But multiple regression, it's additional independent variable as it goes, okay? So still we have a one baseline alpha intercept, but we have a multiple slope along with the number of independent variables. So multiple regression model had multiple independent variables with the corresponding slope for each independent variable. That is the overall equation model. So regression model, especially multiple regression model, we wanted to know now whether this whole equation model is statistically significant or not, how we can confirm it. That's the F test that I left from the discussion. I left the discussion from last week. So let's just move on to the real world examples here. Okay. It had been some government sponsored and then some of the education departments effort that uh, how the college students or high schoolers they can manage their mental stress. Okay, it's still ongoing effort, ongoing research focus. All right. There are a variety of the factors that contribute to mental stress or the mental health for the young adults. All right. So these days there are a lot of pressure about finding job and high expectation and family problems and unexpected just uncertainty about the future, and there might be a lot of the factors. So it is hard to just have only one predictor and only one factor how we can determine the young adults mental stress. Okay, so there should be at least two, three, four, depending on how comprehensive the study is supposed to be. So at least through last 2, 3 decades research done in the field. Scholars and then the education specialists, they found out that young adults' mental stress and depression, the two main variables, the two main factors and indicators of mental health, it's usually caused by their socioeconomic status, especially young adults who are more struggling with, the financial support. It's gonna increase their mental stress. All right, and also psychologists and sociologists they confirm that young adults, especially when they have some traumatic life events earlier in their life, it is more likely to have some lag defect in their mental status. Okay, so then I do not want to ignore one over the other. Since these are two most prominent independent variable, so I want to plug in here again. Don't worry about this scatter plot. Okay, this is not required at all for the this coming Thursday project in the assignment. This is just to show where how they are spread out overall. So these things it's not for descriptive statistics, it's for single each individual variable. That is the assignment for Thursday. But once you just try to find some relationship, then you can use this types of scatter plot and graph. So it's for the main analysis, not descriptive analysis for the individual variables. Okay, that what I wanted to confirm, because Rahul, you wanted to do far beyond what it is expected for the next stage of the work and project. So we can just this line really show that the young adult when they have more traumatic, life events and earlier on, they're more likely to have the mental stress. If their socioeconomic, status increases, their stress tend to go down. All right. So we can see by overall, scatter plus sometimes, but we wanted to make sure it is statistically significant or not. So, so we call that as the partial regression plot. Okay. So it showed that, oh, there's a positive line. Oh, this is a negative line. And again, just it's a little bit of a review for correlation test. Okay. Correlation test, you can find a correlation line that is a standardized slope. So it is a standardized value from -1 and +1. But uh, simple regression model and multiple regression model, these regression plot and slopes are mostly depending on the unit of analysis, right? And also in multiple regression model, they also depend on other independent variables that we try to control for the equation model. So we call that as a partial regression line or partial regression plot or partial regression coefficient. All right. So what you see with the y hat, it's a regression line. And when I put only the number of the traumatic life event, it has a positive, okay, depending on the unit of analysis, that is the coefficient and slope. And when I put um, the socioeconomic status of a young adult, it has negative effect in on our dependent variable, which is the mental health or stress. Okay, so as what you see, the baseline is different for each independent variable. But when this is a simple and one independent variable with one dependent variable, it's a simple regression model with traumatic life event. Simple regression model with socioeconomic status. Now, I do not want to, one over the other. So I put both of them together as independent variables. Now, the equation model changes like that. So the baseline is different now because we put two independent variables together. So then still human life, there's no way we have a zero stress, right? So the level of stress, the when we cannot consider our independent variable, when we put zero, so those intercept and alpha value will vary by number of independent variables, what independent variables you're gonna put. But as you see, even the coefficient, which is the slope, has changes a little bit. Because why this is changing is because we are controlling socioeconomic status. And then what about the effect of traumatic life event on mental health? And what about socioeconomic status effect on mental health controlling traumatic life event? So when you include or exclude or put it or just take it out, different numbers and different factors, independent variables in the regression model, these alpha and beta, in other words, the baseline and the coefficient slope changes, okay, along with. That's what I wanted to show you here. And then I wanted to talk about what is the coefficient of a multiple determination, okay? So basically it's the the symbol wise and notation wise, it is a capital letter R squared. Okay, so we already know small letter R, that's correlation, right? But when introduce the correlation itself, it's not very intuitive interpretation. So I ask you guys, square value, just use a squared uh, r squared the value, but there it's a small letter r squared. So it's a correlation, and also correlate square the correlation value. That means how much one variable explain about the other variable. So that was the things that I explained it. But the biggest difference is here, R squared value for multiple regression model as a coefficient of a multiple determination. We use a capital letter R. Okay, so that means how much the equation models together. So how much collective independent variables together explain something about dependent variable. Okay, so these are some of the numeric expressions, and if you want to say a formula, so basically all the error Okay, so for your mean value to all the way across all your just changes around your dependent variable by the collection of independent variable. So that's the total square the value, sum of square the value. And then we want to make sure whether our regression model explains something and shows something. So out of total error, and how much error it has from the error by the regression model and divided by total sum of squared. So together what it tried to show you as capital letter R squared the value. So how much the collective or collections of independent variables explain the amount of the the variance explanation by the collection of independent variable. So since everything is squared value, this coefficient of multiple determination value cannot be negative. So the maximum value can go to as 1 and the smallest value is 0. If the equation model does not explain anything, then our square value will be 0. If the equation model from regression analysis explain 100% about your dependent variable, the value will be 1. Okay? So that's the second part of a regression model. So as I mentioned that, it doesn't make sense once, for the simple regression model, we talked about R squared value. So once only independent variable's slope is statistically significant. Of course, the equation model will be significant. But in the multiple regression model, there are several independent variable can be statistically significant, but not all of them. So it is necessary for us to talk about this R square value using F test. So that is the reason. Okay? So, multiple regression model, null hypothesis is that none of your independent variable is statistically related or explains something about your dependent variable. So, null hypothesis is all slopes are 0. They're flat. Okay, nothing to do with the, you know, in the dependent variable. And your alternative hypothesis, you can write up actually multiple ways depending on your purpose of research. But generally, as long as at least one independent variable controlling other independent variable, if it is statistically significant, that equation model is significant. And sometimes keep adding all different independent variable will only increase R squared the value anyway. But if it doesn't make any big differences, rather than having like 20 different independent variables in multiple regression model, it's better to have maybe 5 to 7 or maybe 3 to 4 independent variables explain most of them. So it's more of your choice how you're gonna write up your alternative hypothesis. So, but generally when we use alpha test, the alpha test for the equation model, it confirmed that the equation model it is statistically significant, whether by only one independent variable or by multiple independent variable or all independent variable. We don't know yet. We're gonna confirm that by individual t-test for each slope, but the alpha test using R squared the value, we just looked at whether the equation model is statistically significant or not. Okay, so alpha test what we use is that how much the collection of independent variables explain something about dependent variables. R squared the value divided by number of independent variable. And that is in numerator. In denominator, it's all about error. Errors, and as we went over, that's the foundations of statistics, regardless of which test you use. So the errors are okay. What about the regression equation model? Do not explain Okay, what is the proportion and variability that cannot be explained by the collection of independent variables? So it's gonna be total variability we explain is one, and subtract the, how much actually we explain. Then the rest of them are error, right? So that's the denominator. And then also we use degrees of freedom for error is a total sample size minus how many values we fix for each number of independent variable and with the alpha, which is the baseline. So that is the degrees of freedom for denominator. So sample size minus, okay, the number of independent variables and slope. So number of the b's in betas from the data, and then the a, which is the intercept. Okay, so that is the degrees of freedom. As of what we practiced earlier, in order to read the F distribution table, we need two degrees of freedom, one for numerator, the other for denominator. So this is an F test and the structures of the statistics. Again, I do not really expect that or require you to calculate anything like that, but just to know what the computer software and statistical software does it for you. Okay, so this is what they are going to calculate as alpha value. Okay, so alpha distribution again, we go to back to the ANOVA test and how just we read it, but as a part of the equation model, significance, so we use alpha test. So again, degrees of freedom for numerator is the number of independent variable. Degrees of freedom for denominator for equation model, it's a sample size minus all the slope, okay, the coefficient, and then alpha value. So when just the same logic, when you have a higher statistics, large statistic value, that means you're in the critical region with a lower probability for the null hypothesis. So you can confirm, yes, the equation model explain something significant, a significant amount of information about dependent variable. That's how you can argue that. All right. So let's just conclude. If we have the equation model from the regression model, so this is a multiple regression equation model. So since we have the regression line and first independent variable and second independent variable, just it goes back to the main the original variables we talked about. Just traumatic life events is first independent variable, and socioeconomic class is a second independent variable. So if we plug in all the numbers and alpha value we got is 9.5 from alpha distribution table. That's a way higher than the fine line F value at 0.01 and zero point zero 0.05. So it is in the critical region. So we confirm that this equation model, okay, explain something about young adults' mental health. We can argue that. Okay, so let me show you. This is binary result table. Okay, um, so as you see, this is a multiple regression model, and depending on the style of the reference and journal articles and the book, they use different ways to provide in the table and as a separate regression models. But here, just look at the simple numbers. That's what I wanted to show you here. Multiple regression, when we put life events and socioeconomic status together, okay? And what about life events itself as a one independent variable? So as a separate simple regression model, as well as a separate simple regression model for socioeconomic status. As you see, those baseline changes because we control those variables. And also those coefficient and slope itself has a different values because in multiple regression, the beauty of beauty of multiple regression model is that they control the other variable or other variables to see still the specific variable is statistically significant for your dependent variable. So we have more control power for multiple regression model. But as you see here, okay, actually there's one error in this table. Okay, one error is simple regression model, we do not use R, capital letter R squared. Instead, this value should be small letter r squared, okay, because it's a single independent variable. And then multiple independent variables together, then you're gonna use capital letter R squared. So it should be the lowercase r squared value and lower squared r squared value for a simple regression model because it's still correlation, part of correlations, and take a squared value of that. So just to give you a brief idea is that maybe depending on the scales and unit of analysis, but when your life events, traumatic life events, if there's additional number of traumatic life events, uh, the young adults stress level increased by zero point 0.1. Or you can say, if their socioeconomic status, maybe on the scale of 5 or scale of 7, depending on how it was measured, it is increased by 1 unit. Okay, then their stress or mental stress decreased by zero point zero 0.09, almost a zero point 0.1 point. Okay, so that's what you can say for or make interpretation with these numeric values. But another interesting way is if you add a more independent variable, as I mentioned that earlier, your R squared value only will increase. So when you're gonna decide, okay, no more independent variable, when you achieve enough R squared value without some significant, increase, maybe you do not want to have, like even you have a 40 independent variables. It doesn't make sense, right? It doesn't have any like interpretive power. Like basically everything, if you consider everything, you're more likely to explain it, right? But rather than that, with some limited, amount of information, we wanted to maximize interpretation power and explanatory power. So here, when we only include life events as independent variable, the life events explain about 1.138. So in other words, about 14% of uh, you know uh, the variabilities for mental stress. And when we consider the socioeconomic status, we can predict the level of mental stress about like 16%. Okay, so those two variables together as a multiple regression about 34, so 0.339, so about it's rounding up 0.34 um, percent of mental status or stress or depression can be explained by the combined independent variables of life events and socioeconomic status. That's the interpretation you can use for using R squared value. Isn't that great? Right? So for multiple regression, make sure that you interpret each individual slope and what that means, positive, negative, how they are related. And sometimes using the specific unit, you can explain how much increase and how much decrease. But R squared value, that's a very unique way you can explain how much explanatory power each individual or collection of independent variables together explain about your dependent variable. So that's great information to report. Since we wanted to spend more time on, wrapping up the variable description for each of your project. May, if I can, I wanted to just done theoretical discussion today, and then on Thursday class, I can show you how to run multiple regression model and chi-square test, and right after we can move to each of your project. So let's go over chi-square test. Okay, chi-square test is maybe not the most sophisticated statistical approach or method, but it is alternative statistics that you can run for the categorical variables and nominal variables. Okay, and if we have a interval variables and numerical variables, that really just show more incremental and the sophisticated changes based on the statistical significance. But in social science, and political science research, there are a lot of things. As you see from the secondary data set, they are very much like a subjective measures, yes or no, and highly agreeable, does strongly disagree or strongly, agree. It's a very subjective scales of measurement, right? So sometimes we ended up with, and also by nature of variables, we cannot use some numeric values like gender, ethnicity, and any other socially valued and politically valued variable. So if you ended up with the two categorical variables as your hypothesis, then you should use a chi-square test. So it's a new big changes, right? So it is actually the very first, statistical analysis I cover when both of your independent and dependent variables are categorical and nominal variable. Okay, so let's look at the statistic roadmap. So what I covered, the first part of today's lecture is multiple regression model. So we are here when we have more than one, at least two independent variable, but still both your independent and dependent variables are in our scale. Then it's a multiple regression model. Then what about I unnecessarily or um, just based on the nature of the variables you use? Both of them are nominal, both of the variables are categorical. Then you should come back to here, nominal independent variable and nominal independent variable. So that's a chi-square test. Okay. So this will be uh, numerically uh, simpler in a way, but I wanted to make sure again, I will not ask you, I don't expect anyone can really calculate chi-square chi-squared value from the raw data. Okay, but just I want you guys to know when to use chi-square test, what chi-square tests try to come up with, and how we can interpret the chi-square test result. As long as have that information, that's great, and that's what I wanted to cover, must cover this week. Okay, so let's say we have talk about the gender gap in political um, partisanship. Okay, so when we talked about political ideology, we use as a more interval scale, but when we talk about political party affiliation, whether it's Republican, Democrat, and Independents, right? So it's a specific and distinctive three categorical variable, right? Three categorical, uh, variables, and also man and male. That's a distinctive categorical values as well. So when you just see if there's any sort of associations going on, that's a chi-square test. Okay, so only between two categorical nominal variable, but you wanna confirm some sort of association. This is a keyword. It's a not correlations, not linear relationship. When we talk about association across different categorical variable, that is a chi-square test. So when you have a gender with the party identification, party affiliation, then both are categorical. So that is chi-square test. But here, the important thing for the logic and rational for the chi-square test, we use for chi-square test is a contingency table. It looks like a somewhat frequency distribution table we covered earlier as a part of a descriptive statistics, but uh, just, just slowly follow me, all right? So what we call this is a contingent table. They should have, okay, um, observation, okay, observed frequencies from data that you stored in the table. For chi-square test, we calculate one more values to next to them. Okay, why? Okay, so having the observed frequencies itself, the way you see upper table right here, it's hard to say whether there is any association going on with a lot of just numeric values like that. Okay, but like for example, from the textbook example, if the values really show clear trend, okay, clear association, may you can identify here, for example, the first table here below. Uh, when we compare between different like white versus black and about the opinion yes or no and favor oppose or suppose to decline whatever they ask you the dichotomous categorical answers in this case it's clear, right, regardless of their race category, and they all favor of this opinion. There's no association. Sometimes it's really clear what you can find. It's not hypothesis. It's what you can confirm. But as what you see, it's a clear split, absolute complete split. All whites, they are favor of the opinion or policy. All black samples, they are opposed of the policy. So we know there are clear association between ethnicity and the opinion about the specific topic. But most of the cases, that numbers are not that clear cut. So what we do is that, how are we gonna do? So statisticians, so they decide that it's a categorical variable. Not much things we can do, but we wanted to detect whether the observed frequency, they are independent from each other between two different variables, or those two categorical variables are dependent. That's what we're gonna discuss here. So hypothesis-wise, whether those two variables are not hypothesis-wise independent. Alternative hypothesis that what we want to confirm is that those two categorical variables and nominal variables, they are dependent. How we can confirm that? Okay, so statistics. So if we consider null hypothesis, those two categorical variables are independent each other, what is the expected frequencies? So when those expected frequencies based on independence between two variables, okay, that is significantly different from observed variable. Let's consider that are different from independence of two variable, and then it confirmed that your alternative hypothesis, oh, there should be some sort of dependency between two different variables. So it's a sort of uh, rough decision. Okay, rough decision. Not much things you can say about strength of association or directions of association because there's no such direction you can talk about for a categorical variable. But for chi-square test, what you can say is that how different between expected frequencies and observed frequencies. How you can find the expected frequencies basically by proportion of the row proportion and then proportion. There are expected value. If that is different from observed value, the actual observed frequencies from data, that means we can argue that there's a dependency between two variables. You got that? Okay. So how you actually can find expected frequency? If we assume there's no no dependency, they're all independent. It goes by the ratio of row column proportion. So, for example, female Democrat, the expected frequency will be the total row and value, which is 5777, 577, okay, 577, and column frequencies 444 multiplied by together and divided by total of total, which is a total sample size 980. Okay, so that is a by row column proportion against the total number. So that's how statisticians decide as expected frequency. So if those expected frequency is different from observed frequency, that means that is statistically significant. That means there are some statistical dependency. Okay, so chi-square value, that's how you use it as the symbol. And what you're gonna do is that you actually make sure that there is some discrepancy, but you do not want to have all the cancellation problem. You know, this negative value, positive value, and it cancel them all together. Then it's there are some sort of dependency, but at the end, it's gonna be very small value or no value, zero value, then you cannot detect the dependence. Okay, dependency between two categorical variable. So chi-square value, this is how you actually gonna write up. So somewhat deviated from the foundations of the basic foundations of statistical, analysis. But how that's what usually we compare and looking at the differences. So between observed frequency and expected frequency, in order to avoid the cancellation problem, square the value and divide it by expected frequency. Okay, so this is how you're gonna calculate for each cell, right? Observed frequency, expected frequency squared, and divided by expected frequency. For independent female independence, and observe the frequency, subtract expected frequencies, square the value, and divided by expected frequencies. So for each cell, you calculate that and merge them all together. That's a chi-square test. Okay? So we got the value 7. This is a pretty big, okay? I will show you the graph and then the shape of distribution. Okay, shape of distribution. So chi-square test, when the values are relatively small, that means we observe the frequency is closer to expected frequency. That means your observation is closer to independence between two different variables. When chi-square value is large, that means there are discrepancy between your observed frequencies compared to expected frequencies. That means, oh, there's some sort of dependency and association going on between these categorical variables. Right. So chi-square distribution look like this. Since we square them, okay, none of chi-square value can go to negative, but as your sample size goes up, you see that this chi-square value, chi-square distribution sort of gradually, slowly converted to more of the normal distribution shape. Okay, so for the chi-square distribution, again, you need to know degrees of freedom. Degrees of freedom um, in order to read the distribution table. Okay, so degrees of freedom for chi-square test is so pretty simple because we rely on the contingency table. So the degrees of freedom is row number minus 1 multiplied by column number minus 1. Okay, so can be less intuitive, but it can be just, it can make sense anyway. So that is the degrees of freedom we use to read a chi-square distribution table. Okay. So the chi-square distribution is listed in our textbook on page 659. So if you know the degrees of freedom, and also it has a fine line of um, that chi-square value for like a zero point zero 0.05 alpha value, zero point zero 0.01 alpha value. So if your calculated chi-square values are beyond and bigger than this fine line chi-square value, you can confirm your alternative hypothesis. It is statistically significant that two categorical variables, they are dependent, or there is association between two categorical variables. That's what you can argue there. Okay. So as any other statistical analysis, chi-square tests also require some theoretical assumptions and background, and sort of agreement. We wanted to make sure, since we estimate expected frequencies based on the proportions of row and column, based on the total sample size, we want to make sure that each column, each cell has the independent observation. So if especially like somebody answered that from our example, uh, she or he answered both as independent and Democrat. Chi-square test is not going to work. We want to make sure all these samples and each cell, they are independent each other. None of the individual counted more than one cell. This is the kind of the limitation. So since we only use a contingency table, that's what it required as the minimum. All right. And also we use the sample size and then actual observation. We wanted to have at least some minimum numbers of sample size. So it is not really by saying as a large sample size, but minimum sample size we need for chi-square test and calculation estimation of expected frequencies. We wanted to have at least 5 expected frequencies for each cell. That is required. Okay, so we can calculate then the expected frequencies. That's a reliable number to compare to observed frequencies. Okay, so those are two um, requirements and assumptions. Right? It's not that hard to get that. So, sort of a summary, but I wanted to point out some important matters about chi-square test. Chi-square test, we wanted to make sure it's between the categorical variables, nominal variables. If it is either your independent and dependent variable had a numeric or inverse scaled variable, forget about chi-square. It's only when we have limited scales of categorical variables, then it's a chi-square test. Right? So making sure it's independent random sample and minimum requirement is large enough to test it. So at least the frequency, expected frequency, should have over 5. Right? So hypothesis-wise, it's pretty simple. That's what we can maximize our interpretation, whether based on the chi-square tests, those two categorical variables are independent or dependent. That's what we do. And we talked about how you can calculate chi-square value based on the observed frequencies and expected frequencies. So when you read chi-square value, again, degrees of freedom with the fine line, whether your chi-square value from data, it is larger than the fine line chi-square value at 0.05 or 0.01. Yeah. Or your corresponding probability value is small enough, less than 0.05 or 0.01. Then you can report that, okay, it is statistically significant or not based on um, whether the statistical result is located in the critical region or not. Same manner and same way across all different statistical analysis. Okay, so I wanted to wrap it up. Okay, just pointing out some of those common mistake statisticians or sometimes the news reporters they use for the chi-square test. Sometimes the news reporters they have some statistical background, but they forget about the main requirement and minimum requirement for each statistical analysis. So I see quite a lot of mistakes that those news reporters make. So just think about when you can use a chi-square test and when you cannot use a chi-square test. Okay, chi-square test it's a somewhat least robust test. So make sure if you have a very small sample size of 2, 3, 4, 5, especially less than 10, less than it's sometimes sometimes less than 20, that can be problem if you ended up with expected frequencies less than on even one only one expected frequency for it only one cell, it's still less than 5. You cannot use chi-square test because the independency and dependency is not robust information we can report with the small sample size. Okay. And also it's a common mistake. We need only raw data, raw frequencies, because we calculate expected frequency based on the raw data and raw frequencies. But some like rare cases, they use actually percentage in itself. So some of aggregate values of percentage or average number, the use for chi-square, forget about it. That's wrong test. You need the raw values of frequencies because you need to calculate expected frequency. Okay, in order to get the the chi-square value. So it required the actual frequency, observed frequency from the data set in order to calculate also expected frequency. So if you have aggregate value of like average and percentage, forget about it. It's not for chi-square test. Okay. So I already mentioned that if you have like you can answer these categories and the other category, if it's multiple selections of the choices, forget about chi-square test. It's not gonna work. Each cell and each individual in the sample should be independent across all the cell. That is required. Okay. So then also I want you guys understand that chi-square test can tell you whether there is the way we had a limitations about the correlation test. What you can tell from the correlation test whether there is a correlation between interval variables. Same thing for the chi-square test. Whether there's an association between two categorical variables. That's it. That's the maximum information you can tell out of statistical significance. Then I want to do more. How they are associated. We cannot tell the association, strength of association, but we can explain with the additional information. So once you run contingency table for the chi-square test for expected and observed frequencies, you can add as the aggregate value, as the result, not as the way using the chi-square test, but as additional values, you can calculate the percentage of each cell, row, column percentage. You can use it for interpretation. Okay, so 80% of Democrats are more likely to support that policy. And only 20% of Republicans are less likely to support. So it can give you some patterns of association using cell percentage. That's just some additional information you can use reporting beyond the frequencies of a reporting percentage for each cell for further interpretation. That's a chi-square test. Okay, so I will end our discussion about multiple regression model and chi-square test today. Is there any question? Is there any question, Rahul? Do you have any question about that? So by having that covered on Thursday, and I will go over um, how we can run multiple regression and chi-square tests utilizing the secondary data set with SPSS software. So rest of the time we can spend for individual project. All right. So I will stop today's class right here. But I'll be